This video will have you going in circles. A circle is the locus of points equidistant from a single point. Its radius is the distance from the center to the edge. A chord drawn from any point on the circle through the center to the other side is called the diameter. The circumference of a circle is the measure of the distance around a circle. In essence, it's a circle's perimeter. We'll call the circumference C. In investigating the circumference of any circle and finding the ratio of the circumference to its diameter, we find that it always equals the same number. This number is called pi. Pi is the most famous constant in mathematics, and the circumference formula is given by circumference is equal to pi times diameter, or 2 pi r. In high school, my teacher told me to remember circumference as cherry pie's delicious. C equals pi times diameter. But now what about the area of the circle? The measurement of all the two-dimensional space inside the circle's edge. Well, let's think about how we find the area of a regular polygon. A regular polygon is a polygon where all the sides are the same length, an equilateral polygon. And its area formula is given by 1/2 its perimeter times this thing called the apothem. The perimeter of a regular polygon is easy to find if all the sides are the same measure. So if there's a polygon with n sides, its perimeter is equal to n times s, where s is the measure of one of the sides. Now the apothem, by definition, can also be called the inradius, and it's the distance measured from the center of a polygon to the midpoint of one of the sides. The apothem will always be perpendicular to the side. Here are a few examples of apothems in some regular polygons. Now we can also define a radius for a polygon, a regular polygon that is, and that would be the distance from the center of the polygon to one of the vertices, that is one of its corners. So there's a slight difference between the apothem and the radius of a polygon. One goes to the midpoint of the side, the other to the vertex. Here's an example of what I mean. So the area formula is derived for any regular polygon from the idea that any regular polygon can be split up into triangles. And so the apothem and the radius and the side of the polygon all form parts or sides of the triangle. And using the area formula for a triangle, 1/2 base times height, we can deduce the area for the entire polygon. Now, if you recall, the perimeter for a circle is its circumference. And if area is equal to the perimeter times the apothem, we can replace perimeter with circumference. Area equals 1/2 c times a. And for a circle, the apothem and the radius are one and the same. So therefore, replacing a with r, we get 1/2 the circumference times r. Remembering that the circumference can also be written as 2 pi times r, the 2 and the 1/2 would cancel each other out, and we can absorb the r's together, giving us r squared. And thus we have the formula for the area of a circle, pi r squared. And there it is, that constant pi, once again. It's in the circumference formula, it's in the area formula. Now if we consider the area of many regular polygons, and we think about increasing the number of sides, what we get eventually looks just like a circle. So if we think about this idea of increasing the number of sides of a polygon, a regular polygon, and calculating its area each time, then we get closer and closer and closer to calculating the area of the circle. This idea is called a limit, and it's the backbone for defining things in calculus. Now, area of a regular polygon is 1/2 perimeter times apothem, and the perimeter is the number of sides times the length of the side. So we can say NSA divided by 2 is the area. Now, taking the limit of something like this as the number of sides goes to infinity, meaning that as we go to a circle, this limit would reach pi r squared. And this is a little difficult to see, especially if you're aware of limits. So there's another formula for the area of a regular polygon involving trigonometry, which becomes very useful. And here it is. N, the number of sides, divided by 4 times the tangent of pi divided by n. So that formula becomes very useful if you have a very large regular polygon. So now, pi is a real number, but what does that mean? Well, let's take a look at a few kinds of numbers first to get a sense of what numbers are like. We have the natural numbers, 1, 2, 3, 4, etc., and these are also known as the counting numbers for obvious reasons. Next, if we include 0, if we invite 0 to the party, then we get what are known as the whole numbers, 0, 1, 2, 3, 4, etc. Now, after a while, we wind up needing negative numbers, so if we let our whole numbers also have negative signed partners, then we get the set of numbers known as the integers, indicated with the letter z, 0, plus or minus 1, plus or minus 2, etc. Next, if we take any integer and divide it by another integer, we get what is called a rational number, a fraction, essentially. Any number of, or any ratio of two integers where the two numbers, the two integers, have no common factors. These are all examples of countably infinite sets of numbers. Sets of numbers that can be ordered or enumerated. In other words, we can assign a label to every one and count them even though they are an infinite set. So then that begs the question, are there uncountably infinite sets of numbers? Spoiler alert. The answer is yes, there are. The numbers that we can find, let's say while measuring the sides of a right triangle, as did Pythagoras, they lead to irrational numbers. For example, the square root of 2. So there are numbers that are not rational. To get a sense, take a square and create its diagonal. If you solve the Pythagorean theorem for the length of this diagonal, you wind up getting a multiple of radical 2, a multiple of the square root of 2. And so if we let the sides of the square equal 1, the diagonal is square root of 2, an irrational number. So we have these numbers. We have natural numbers, we have whole numbers, we have integers, we have rational numbers, and then of course we come across these other numbers that are irrational numbers, not rational. So all of these numbers together form what are called the real numbers. So some examples of irrational numbers are like the square root of 2, the square root of 3, or the golden ratio, 5. We also have other numbers like pi and e. And they come in two flavors actually. Algebraic numbers and transcendental numbers. So irrational numbers can either be algebraic, and what that means is that these numbers can be algebraically reduced down to 0. And we'll show you what that means in a moment. Transcendental numbers are numbers that cannot be reduced down to 0 with a finite number of algebraic operations. So it separates irrational numbers into two classes. Consider the square root of 2. We can square this and get 2, and then subtract 2 from this and get 0. Or the golden ratio, 1 plus radical 5 over 2. We can multiply by 2, subtract 1, square both sides, and subtract 5 and get 0. These numbers are algebraic. Pi, however, we need expressions here to represent pi and to estimate pi, as well as e. So here's e. This one is a little bit more well known amongst the mathematics community in terms of expressions. So here we have an infinite series that can be used to tell us the value of e to a certain degree of accuracy. But we could never write down the entire number. It's an infinite series that is convergent, but convergent to a transcendental number. This all goes back to that same idea of a limit. So the real numbers, they consist of all numbers that are both rational numbers and the ones that are irrational numbers. And as we've seen, some of those irrational numbers are algebraic and some of them are transcendental. Our friend pi is amongst the transcendental. Real numbers are best understood through decimal representations, that is, placeholders of powers of 10. So, for instance, 1/3 a rational number as a decimal is 0.3 repeating. The pattern is a repeating pattern of 3's after the decimal. Similarly, for 1/2, which is 0.5, or 0.5 with zeros repeating after it, the 0 is the repeating pattern. But for irrational numbers, this is not the case. They do not have a repeating decimal pattern, nor do they seem to end. For instance, our friend pi. Here's a few, 100 digits of pi to show you that it really looks somewhat random in the way that these numbers are generated. Doesn't seem to be a pattern in sight. So you can actually prove that pi is an irrational number, and proving an irrational number is in fact irrational can be easy if it's an algebraic number. So for instance, the proof of the square root of 2 being an irrational number starts as a proof by contradiction. You start off by saying, hey, let's let the square root of 2 be a rational number. Let's assume that it is, where it's a fraction a over b who have no common factors. So then squaring both sides of the equation you've written down, you get 2 is equal to a squared over b squared. And bringing some terms to the other side, 2b squared equals a squared, which then implies a is an even number. So writing it as an even number, or 2 times some integer, we can then rewrite this equation as 2b squared equals 4m squared, or b squared equals 2m squared. This implies b is also an even number. This is a contradiction because originally we said that the two factors a and b did not have any common factors. So if they were both divisible by 2, that says that they have a common factor of 2, leading to a contradiction. Therefore, the square root of 2, our assumption, is false. not a rational number. So we say that the square root of 2 is irrational. Now, however, the proof for the transcendental number pi being irrational is much more difficult and requires calculus. There's some nice proofs of this on the internet, but maybe I will leave this for another time and I'll make a video for that. So there it is. Pi. It's real, it's irrational, it's transcendental. What's more to like? And it's delicious. Happy Pi Day, everybody.
3.141592653589779322383209749458219715128828993628034825 342117067. That's 100 digits of pi. Happy Pi Day.